Okay, I'm going to pick up here where we left off, working through this reaction of lead nitrate with potassium chromate. So we've completed the total ionic equation again by evaluating solubility rules, identifying whether combinations of cations and anions would be soluble or insoluble. We determined lead chromate was insoluble, so it's a solid here in our ionic equation because it's not separated into pieces in the solution. The lead and the chromate are together in the solid, but the nitrate ions and the potassium ions, and there should be a 2 there in front of potassium. I was in a little bit of a hurry there to make sure the video wasn't too long, so don't forget that 2. 2 potassium cations, they are still dissolved in solution, so they are still ions. They're still floating in this aqueous solution of water that we have going on. Now, the next step here I would usually do is, now that I've got the total ionic solution, I would use that information to help finish off the first version of the equation here, where we had this introductory data, which is the molecular version of the equation. Now, we've predicted the products here, lead chromate and potassium and nitrate. Since we already wrote lead chromate in the correct molecular form, that is exactly how it will appear here in the molecular equation. Right? And we do, again, still have to make sure that it's a solid. Any components that are still soluble on the product side, we need to imagine them as a molecule so that we can write them as a molecule back here in the molecular equation. So if I made a molecule out of potassium and nitrate, potassium's got a +1 charge, nitrate's got a -1 charge, the correct formula would be KNO3. Right? And I would want to indicate that that is aqueous because we've already determined potassium and nitrate will not form together and become a solid in our solution. They'll remain ions, but that's not how we write it in a molecular equation. Now, to make sure the equation is balanced, I can't forget these 2's here, so that 2 should go out in front of potassium nitrate. Right? So again, I mentioned the importance of the polyatomic ions and writing formulas we talked about in chapter 2. That is relevant here for finishing off your equations as well. Do not call this K2NO32. That's not the correct way to write the formula. That's not the correct way to put it into an equation. You've got to recognize what's the right way to write the formula, and then you've got to use your coefficients to make sure your equation is balanced, just like we talked about in chapter 2 and then in chapter 3. Now, there's actually one more version of the equation here that we want to think about, and that is called the net ionic equation. And let me mention, because it just occurred to me that I probably should, some textbooks use complete ionic equation instead of total ionic equation. Right? That's not too big of a leap for you to recognize those are describing the same thing, total and complete being synonymous in this case. And I'm not really sure which one our textbook uses. So if you see complete ionic equation, that's the same thing as the total ionic equation. But the net ionic equation is meant to just focus in on the parts of our equation, the parts of our mixture that undergo a change over the course of the reaction. So what we want to do to figure out the net ionic equation is identify what are called spectator ions. So let me put a little definition over here. Spectator ions. Spectator ions have no change in phase over the course of this type of reaction. So that means they would have the same phase on the reactant side as the product side. So in this particular reaction, nitrate is aqueous as a reactant, aqueous as a product. It's a spectator ion. Same is true for potassium. The potassium cation is aqueous as a reactant, aqueous as a product. So let me put a circle around those. Nitrate, potassium, nitrate, potassium, those are spectators. And just like in the sense of, say, a sporting event, right? A spectator is there watching, but not taking part in the game that is, that people are there to watch. So these ions are just hanging around watching the actual reaction that occurred. Now, the parts that do change phase are going to be the ones that appear in our net ionic equation. So it's just this sort of description of the changes that happened in the reaction. So lead is aqueous on the reactant side, chromate's aqueous on the reactant side, but they're both part of the solid on the product side. So that is our net ionic equation. The lead ion, and again, we've got to have the right charge, we've got to have the right phase indicator there. If you leave those off, you have not correctly written this equation, is going to react with the chromate ion to make the lead chromate solid, right? And that would be our net ionic equation for this reaction, because really nothing has happened to the nitrate and the potassium. They are in our equation, but if we want to focus in on just where the changes are, it's the formation of the solid. Okay, now we want to try a couple more of these just to give you an idea. It's fair to tell you there'll be something like this on the test, right? And all I'll give you is just the two reactants and expect you to be able to complete out everything, every charge, every phase indicator, the correct formulas, predicting the solids, all of it. You should be ready to do that. So let's look at this one. Now, we want the same equations, molecular, total ionic, and then net ionic for this one. So we start off with FeCl3, right? Again, based on the charge on chloride, we could recognize that this is iron with a 3+ charge, and chloride is an anion on its own, so there'll be 3 of those with a -1 charge in that solution, right? And in this case, we're kind of given that's aqueous. We could figure that out, though. We know from solubility rules, chloride salts are usually soluble. Iron 3 is not one of the exceptions. So even if we weren't told that that was aqueous, we could figure out that it should be aqueous from its formula. Sodium hydroxide is also aqueous, but again, we could figure that out from solubility rules. Sodium salts are always soluble, even though hydroxide usually is insoluble. Sodium is one of the exceptions. Now, got a little hint here that we need 3 sodium hydroxides. You won't always get that hint, but now that we're just learning, we'll take that hint. 3 sodium hydroxides would mean 3 sodium cations are going to end up in this solution, and 3 hydroxide anions will end up in this solution. And again, you've got to know your polyatomic ions to know hydroxide is going to still be hydroxide even when the compound dissolves in this particular reaction. Okay, once we have those ions, we can think about identifying what product might form here. So iron was soluble with chloride, right? Cation's not going to react with another cation, but iron and hydroxide, right? We said hydroxides are usually insoluble, right? But sodium was an exception. Iron is not an exception. So iron hydroxide is going to be a solid here. It's going to be insoluble. And what we have to get is the right formula. Since the iron's +3, hydroxide's -1, the correct formula here would be FeOH 3 times. That would be our solid. Okay. Now, the remaining ions in solution would be sodium and chloride. Well, sodium salts are always soluble, so sodium chloride, they're going to remain dissolved. They're going to stay aqueous, they are going to stay soluble, they're not going to form a solid. So we would still have 3 chloride anions and 3 sodium cations on the product side of our reaction. Okay. Now, once we finish this total ionic equation, that should allow us in a fairly straightforward manner to finish the molecular equation. We already figured out the right molecule for the solid there. Iron hydroxide is going to be a solid. Right? Now we want to make a molecular formula out of our remaining cation and anion. Na is our cation, Cl is our anion, +1, -1. We just need one of each. So the correct formula there would just be NaCl. Right? But we would want to make sure we list that as aqueous. And again, remember the cation comes first, right? Or the metal, it's metal cation. So it's NaCl, not ClNa. So get that order correct when you're putting together your formulas as well. Because there was 3 of each, though, the 3 would end up in front. And I see a lot of times people will do Na3Cl3. That is not correct, right? You ruined your equation there if you do that. So make sure you follow those same rules we talked about before. Okay, now I think we have just enough time to finish the net ionic equation here. The spectator ions, chloride and sodium, are soluble on the reactant side, soluble on the product side. They're the spectator ions. We'll leave those out of the net ionic equation. The net ionic equation will be iron cation reacting with the 3 hydroxide anions to form the iron 3 hydroxide solid, right? And again, notice the parentheses, and where the 3 goes outside the parentheses, you want to make sure you get that correct in your version of the equation as well. Okay, one more example in the next video, and then we'll move on to the next page.